Welcome to the series Mud Talks, Secrets of the Hidden Universe with Professor Brian Shuve. My name is Vanessa Chu, Assistant Director in the Office of Alumni and Parent Relations. We thank you for attending today's event, and we hope you and your family are safe and healthy during this time. This talk is being recorded and will be distributed along with any presentation materials after the event. Please feel free to type your questions in the Q&A box, not the chat, and we will try to get through as many questions as we can after the presentation. Now, to briefly introduce our speaker, Brian Shuve is an assistant professor of physics at Harvey Mudd College and conducts research in theoretical particle physics and cosmology. He joined the HMC faculty in 2017 and is passionate about making research in particle theory accessible to undergraduate students. He is also committed to equity in physics and has been involved in diversity, equity, and inclusion efforts locally and in the broader physics community, including as a member of the Particles for Justice Collective. I now turn it over to you, Brian. Take it away.
Great. Thank you so much for that wonderful introduction. And thanks to everyone for coming. I know that we're all a little bit overloaded these days. I appreciate the time that you're taking to spend with me. So today I'm going to be telling you about one of the most persistent mysteries in the universe. What is dark matter? And you may never have even heard of dark matter before, but it turns out that the universe is full of it, and we don't know what it is. Since most of our understanding of dark matter comes from outer space, I want us to start our journey in our cosmic neighborhood, which is the Milky Way. So this is the Milky Way. We can see it from Earth on a clear night, usually not in LA because of either air or light pollution, but if you can get up into the mountains, you can see it. And it is a collection of about 100 billion stars. The sun is just one of those stars and is a pretty typical one. And we're living out here in sort of an ordinary arm, quite a far away from the center of the galaxy. It takes light about 30,000 years to get from the center of the galaxy to where we are, which gives you some sense of the scale of this object. And it's full of all sorts of really fascinating things, stars and planets, and in our case, human life, but also things like nebulae, supernovae, black holes, all sorts of really cool stuff. And everything that we see here is made up of the same atoms that make up you, that make up me, that make up the desk that you're sitting at, and so on. And so this is what we usually think of when we think of outer space. But in this talk, what I want to do is dig a little bit deeper and think about what's actually present. So this is what the Milky Way looks like if we could see this mysterious substance that's called dark matter, which I've put here in sort of a blue animation or coloring, but you can't actually see it. It's invisible. So my colleague and friend, Dr. Chanda Prescott-Weinstein, sometimes says that dark matter is a bad name for it, that a better name would be invisible matter or clear matter. And we're completely immersed in it. It's in your room with you right now. In fact, every second, about 1 trillion dark matter particles are passing through your body as we speak. But it's something that we can't see with our eyes. It's something that we can't touch, smell, use our normal senses. And what's even more remarkable is that it turns out that there's a lot more of this dark matter than there is of us. In fact, of all the matter in the universe, about 85% of it is dark matter, and only 15% is made up of the regular matter that we see in stars and gas and planets. So you might ask, how do we know that it's there? And the way that we know that it's there is that this dark matter exerts a gravitational pull on the regular matter. So when we see stars and gas moving through our galaxy, it's being tugged on by dark matter, and we can figure that out. So there are a bunch of questions that come to mind from this that I'm going to address in my talk. The first one is a question you might be having, which is, how do we actually know that dark matter is there? I kind of sketched it out a little bit, but it seems a little bit hard to believe that all of this stuff could be there and for us to have not known about it until recently. The next question that we could wonder is, what is it? Right? If it's not made of the usual atoms, then what are the candidates for dark matter? And then finally, of the possibilities for dark matter, how can we make progress in figuring out what dark matter is and what it's made of? So I mentioned that we know about dark matter through its gravitational pull. And so I want to start with a more familiar example. So this is a picture of our solar system, the objects not drawn to scale, with the sun at the middle and planets moving around it. And we can see from this animation that here on Earth, we go around the sun once in 1 year, and then there are other planets, asteroids, and so on that are going around. And the orbits of these objects are determined by the gravitational pull of the sun. So when you're closer to sun, gravity acts such that the force is stronger, and this leads to a higher speed in terms of its rotation. Whereas the farther away you are, the smaller this force and the slower the rotation. So we see, for example, that in the time it takes Earth to go around the sun once, when we look at other planets like Jupiter or Saturn, they're really not making much progress at all. So if you happen to have taken a first-year mechanics course, this is a problem that we love to ask, namely to say, okay, well, if you have something that's moving in a circular orbit, can you determine its speed given the mass of the sun and how far away it is? And if you do the calculation, this is the formula that relates them. And so we see indeed that as the distance gets larger, the speed of the objects gets smaller as we get further away. This also actually provides a way for us to measure the mass of the sun, that if I know how fast, say, Jupiter is moving and I know how far it is from the sun, then I can reconstruct the speed. So what happens if we now apply this to the galaxy as a whole? So our Milky Way galaxy is called a spiral galaxy, and it's also rotating. So we are orbiting the center of the galaxy just like the Earth is orbiting the sun. And it takes a really long time for the galaxy to do one rotation. It takes about 250 million years. But still, we're moving actually very fast relative to the center of the galaxy. And a similar rule we expect to apply due to gravity, that when you're close to this concentration of stars and gas where we think the mass is concentrated, we're going to be rotating faster. And then when you're really far away, then you expect the force of gravity to be weaker and you're rotating slower. And this is what's given by this red curve, which is that based on the presence of stars and gas in the galaxy, we can make a prediction for how fast objects are rotating the farther out you go. We can then do measurements of this rotation and see what happens. And that's given in this white curve here. And you can see that they actually disagree really significantly. In fact, it seems that the farther out you go, you don't slow down at all in the orbit. So this would be almost as if Jupiter or Saturn were going just as fast around the Earth, around the sun as the Earth is. So this doesn't seem to square up because all the mass is here and the law of gravity says the farther out we get, it should be rotating slower, but that's not actually what we observe. So what we can infer is that there's actually more matter than we thought to explain why there's this discrepancy between the fast rotations of stars and gas that we see out here and the slow rotation that we would expect from gravity. And in order to make this work, we have to have this giant cloud of matter that we don't see from visible light. And this giant cloud actually has to extend way far out beyond the outer where we think the edges of the galaxy are in order to explain the orbits that we see. So by taking an analogy of the solar system and trying to measure the mass of our galaxy, we find that there's a discrepancy between the light that we see and what gravity is telling us the distribution of the mass is. I do want to say a little bit about how this discovery was made. So Vera Rubin and her collaborator Kent Ford in the 1960s and 1970s developed a new pioneering method for measuring the velocities of stars by precisely determining the color of the light that was emitted by those stars. And this was really the first significant evidence that people really believed for the existence of dark matter. She's notable for a number of reasons, of course, for this discovery, but another one is that she is a member of a long line of really outstanding women astrophysicists and physicists who were not awarded a Nobel Prize for their groundbreaking discovery. But we can take some consolation in the fact that one of the premier observatories was just renamed the Vera Rubin Observatory, and so a lot of the new knowledge that we'll be gaining about the cosmos will at least recognize her important contributions. Now, it turns out that this is not the only way that we know the dark matter is there. If it were, maybe we just made a mismeasurement or there was something off. I want to now tell you about a different way that we can determine the existence of dark matter, and it's through something called gravitational lensing. So what's gravitational lensing? First, I have to tell you a little bit about our modern theory of gravity, which is the theory of general relativity. And you might think of gravity as some like weird invisible force that just pulls things closer together, that makes an apple fall off a tree and hit you on the head. But we now know that gravity is not actually a force, but it's a manifestation of the warping and curvature of space itself. So what do we mean by that? What we mean is that the Earth is so heavy that it distorts the space around it. And so instead of thinking of there being like a little rope that the Earth is pulling on, say, a satellite, it's actually the satellite is moving through this warped space, and that's what leads to what we think of as the gravitational force. So how is this relevant for dark matter? Well, the distortion of space only depends on the total mass that you put in there. It doesn't matter whether it's a planet or dark matter or anything else. And there's a really striking effect of this curvature, which is called gravitational lensing. So what does that mean? Well, let's imagine we have a distant galaxy here, and then we have another galaxy that's in front of it, and this galaxy is bending the space around it. Light likes to travel in straight lines, so we have light from this distant galaxy that is reaching us, but its path is being curved because it's going through this distortion. And we know what happens when light travels on curved paths. This happens, for instance, if you have glasses and you have curved pieces of glass that bend the light. This leads to lensing. And this means that we see really funny distorted pictures of light. So this is an example of a galaxy cluster. And these streaks are not like somebody had some droplets of water on the lens of the telescope or something. This is actually the pattern of light. And these blue streaks are all the same galaxy. We're seeing multiple copies of the same galaxy, almost like a fun house, except instead of glass and mirrors, this is happening because of the distortion of space from this galaxy here. And we can use this to make a measurement of the mass. So this is a cluster of galaxies, so a collection of galaxies called Able 1689, which this image was made by the Hubble Space Telescope. And you can see, it's a little bit harder in this picture, but these streaks, like this one here, is another manifestation of lensing. So we can use this lensing to figure out where the mass, the heavy stuff in this galaxy is. And those regions are shaded in purple, whereas the light-colored yellow spots are where the visible light comes from. So this is where we see stars, but in this middle region, we don't see stars, but we still see a lot of matter. And this is where the dark matter is once again hiding. There's this giant glob of it here that's surrounding the galaxies that we do see. And also worth mentioning, this galaxy is 2 billion light years away, which means it took 2 billion years for light to reach this galaxy. And so we're sort of seeing a snapshot into the past, and that's telling us something that dark matter was also around back then. This is just a couple of examples. It turns out that there's a huge amount of evidence in favor of the existence of dark matter. We see it, not directly, but through its gravitational pull. And its effects span the entire age of the universe, starting from 10 seconds after the Big Bang, when nuclei started forming, through to when proto-galaxies started clumping because of dark matter forming kind of a backbone around which the rest of the galaxies formed, through to even, seeing dark matter before atoms were formed. So this convinces us that it's not just one little anomaly, that we're really seeing evidence for this hidden or invisible matter everywhere we look. And there are a few things that we can collectively determine about what dark matter is from the collection of observations that we're showing here. So the simplest one is that it exists, or at least, to a very high confidence level, we're almost certain that it exists. But there are a few more things that we can say than that, even if we still don't know very, very much about it. So one of these things is we know the total amount of dark matter in the universe. We know that dark matter, if we add up all of the bits of it, are 85% of all the matter. And that's actually, we know that to about a percent level accuracy. So this is something that we can determine very precisely. Another thing that we know is that it has to be stable. And I said, okay, well, we see evidence for dark matter from billions and billions of years ago. If dark matter was something that could vanish or decay or disappear somehow, then that's bad because we see it still hanging around today. We know that dark matter doesn't interact much with regular matter. And this is now going back to something that I said earlier about the fact that there are these trillions of dark matter particles hitting you every second. And the fact that we don't notice that and that we don't see it in our visible light tells us something that dark matter has to be pretty far removed from these regular interactions with light. The last thing is a little bit different from what I showed you in the original examples of galaxies and where dark matter is in the galaxy. But it turns out that dark matter really forms the backbone of galaxies, and the galaxies wouldn't be created in the ways that they do if there was no dark matter. And so these clumping properties of dark matter to form the galaxies that we see is very important property for these particles. And this is about it. It's not really very much to go on, but at least it's something. And so when we're assessing ideas of what dark matter could be, we kind of go down this checklist and see whether it works or not. So hopefully I have convinced you that dark matter exists, or at least that there's something really weird that's going on, that we need to add something to our current picture. So the next natural question is, well, what is it? Because I've been making it sound very mysterious, and so we want to know, is it just a different rearrangement of the particles we know about? Is it something that's completely new? Yeah, what is it? So before we get into that, it's probably a good idea to review what we're made of, because I keep using words like regular matter and visible matter to contrast it with dark matter. But we should say what regular matter is. So what we can do is take ordinary objects. So for example, I'm sitting at a wooden desk. Actually, it might be a fake wooden desk, and I'm not actually sure. But if I were to cut it open and break it up into little pieces, I would find that the structure of the material is determined by molecules that combine together to form metals or wood. And that these molecules are made up of individual atoms, which for a long time were thought of as the smallest pieces that you could make. But we now know that these atoms, and you may have learned this in a high school chemistry class, can themselves be broken up into smaller pieces. So atoms are made up of electrons, which conduct electricity and kind of live in this haze on the outer reaches of the atoms, and a nucleus, which sits at the center of the atom, which consists of protons and neutrons. And we now know that the protons and neutrons themselves can be broken up into smaller things, which are called quarks. And as far as we know, this is as far down as we can go. We've never seen whether quarks are made of anything smaller or electrons made of anything smaller. As far as we know, those are the basic building blocks. Now, it's not enough to just talk about the bits that go into regular matter. It also matters how we assemble them, or how they get stuck together to make the atoms and molecules and structures that we see. And it turns out that there are three forces of nature that affect the particles that we see. The one that you've probably seen before is the electromagnetic force. So this is responsible for things like electricity that powers your computer, magnets, and also light. There are two others which are more removed from our day-to-day experience. There's something that's creatively called the strong force, because it's strong. It's basically like sticky tape, and it's the force that's responsible for having the quarks stuck inside of protons and neutrons, and for sticking the protons and neutrons together in the nuclei of atoms. There's another force, also creatively named the weak force, and it's called that because it's weak. It doesn't have much effect, and the sort of best manifestation that you might be aware of is in the processes of radioactive decays, that when we think about things like uranium or other heavy elements that are undergoing nuclear decays, that's often the result of the weak force. I'm not here talking about gravity, and you might be wondering why. I mean, gravity was really important. But on the scale of subatomic particles, gravity is actually almost completely negligible. Right? So gravity is important because we happen to be sitting on a gigantic rock called the Earth, and that happens to be close to like an even bigger thing, which is the sun. But if I'm just looking at two electrons, the gravitational attraction is almost nothing between them. So far, we have these building blocks that we can use to understand the composition of matter and then the forces that stick them together. And collectively, this is called the standard model of particle physics. And it's essentially a collection of Lego pieces and recipes for putting them together to make the things that we see, whether they're stars and gas or your refrigerator or anything. So here I'm showing the known matter particles of the standard model. So these are the things that make the stuff that we are aware of, starting from the quarks that form protons and neutrons. And they're kind of organized based on how much they interact or how sticky they are. So the quarks feel the strong force, and so they really like to stick together. As we go down in this table, we start finding particles that interact less with each other. So if we go down, probably the most familiar one that you might recognize here is the electron. This is something that feels the electric force, but it doesn't feel the strong force. And then if we go even further down to the bottom, we find a collection of particles called neutrinos. And these are special because they only feel the weak force. They're not electrically charged. They don't feel the strong force. They only interact very weakly. And if you see anything in the news, they sometimes talk about ghostly particles that are neutrinos. That's these things. And they're called ghostly because they also just pass right through your body and you wouldn't even know. So on the order of trillions per second. Now you might notice that there's actually a lot of different particles, and we find that the particles in the Standard Model form three, we call them generations or families. And basically what that means is as you go to the right, you find particles of identical property, but that they're heavier. So for example, the electron is a negatively charged particle. The muon is also a negatively charged particle that's identical to the electron in every way, but it's heavier. And the muon will come back in a little while, so keep that one in mind. But then there's an even heavier cousin of both of them called the tau. But otherwise they're the same. We don't really understand why it's this way, and the structure is not super important for my talk. The important thing is that as far as we know, everything can be built out of these matter particles. In a quantum theory, we now know that each of the forces has an accompanying particle as well. So what does that mean? Well, what we mean is that if I have, say, positively and negatively charged particles, instead of thinking them as just sort of magically attracted to one another, we can think of them as firing particles at one another that cause them to be attracted to one another. And in the case of the electric attraction, the particle is called a photon. This might be, again, something you've heard of. It's a massless particle that travels at the speed of light. But each of the forces has one. So the strong force has something called a gluon. The weak force carriers are called the W and Z bosons. But these are associated with implementing those forces that stick the particles together. And then the last one here is called the Higgs boson. And this is the most recent addition to the Standard Model. This was only discovered a little under 10 years ago. And it is responsible for giving mass to all of the other particles in the Standard Model. And I'm not really going to have an opportunity to talk very much about this, but if you have questions about it, we could have some interesting discussions about that. So if this is all a bit much, that's fine. It is a lot, but the important thing to keep in mind is that this is taken together can explain everything that we see on Earth and that we can create in the lab. So a natural question that we might have is, okay, well, can dark matter be made of any of the same things that we're made of? So if you'll remember, we have this list of requirements that dark matter has to satisfy: how much it is, that it's stable, that it doesn't interact too much with regular matter, and that it's cold or that it clumps in a certain way. So what I want to do is go down that list, and we're going to cross off the particles in the Standard Model that can't be dark matter. So that's why I have here what isn't dark matter. So let's start with the first one. We want particles that could be dark matter to not interact very much with other things, okay, because they pass right through us. So this immediately rules out anything that feels the strong force or the electromagnetic force. So already we're not in great shape. We've just thrown away, how many is that? 12 of the particles of the Standard Model. These can't be dark matter because we would have seen them, we would feel them bump into us. Another requirement is that dark matter is sufficiently stable that it lives to the present day, which is about 14 billion years after the Big Bang. And so we can use that to cross off the Z boson and the Higgs boson, both of which decay in a tiny fraction of a second. So there's no way that they would last for this long. So what we're left with are these neutrinos, which I refer to as these ghostly particles that pass right through you, and you might think, oh, that's great, maybe this is what dark matter is. But unfortunately, these neutrinos have a mass that's too small, so that if we add up all of the neutrinos in the universe, they can't possibly add up to the total dark matter mass that we see, and they don't clump in the right way. So if you're following, you will notice that we've now crossed off every single particle that we know about. And so what this tells us is that dark matter has to be something new. It can't be any of the kinds of matter that we currently know about or that we understand. So this is both troubling, but it's also exciting. As a particle physicist, what this tells us is that the universe is full of stuff that's totally different from anything that we ever have seen before. And that means that we have a chance to really learn a lot about what makes up the universe on a really fundamental level. Now, there are a lot of models for what dark matter could be. So I would rather just discuss some maybe mindsets of the way that we think about what dark matter could be. So the first one I want to talk about is the idea of dark matter that would be favored by a minimalist, okay? Someone who likes Marie Kondo, somebody who likes to keep things simple. And often the people who propose this minimalist scenario are people who really embrace Occam's razor, which is the statement that probably the simplest answer is the right one. So what a minimalist would say is, okay, well, we don't have a particle that can be dark matter, but we have these neutrinos that are like almost good enough to be dark matter. So let's just tack on a particle. And this is going to be the missing dark matter. And now we will have a complete story of what makes up the universe. And there's nothing wrong with this perspective. This is a perfectly valid one. And what's nice about it is that it's very predictive. Because we're only adding one new thing, then we can use what we know about dark matter to say something about how this has to talk with the rest of the standard model. So maybe it feels the weak force, but it's just like a little bit weaker than the regular neutrinos. Personally, though, I don't know that I find this very compelling. And one of the reasons is that the standard model, our particles that we know about, this is really complicated, right? There's 3 forces, there's on the order of 17 different kinds of particles. They're always bouncing off each other. They're doing interesting things. And remember that all of the particles that we know about only constitute 15% of the total. So it seems a little bit weird to say, okay, 15% of the universe is this really complicated, interesting stuff, and then 85% is just going to be this boring one thing. Something is a little bit off there. And so a different viewpoint, which is maybe for people like me who like to reason by analogy, is to say, well, if there's more dark matter than us, then why can't there be a whole dark version of the standard model, okay, with dark quarks and dark electrons and dark photons and dark gluons, dark Higgs bosons, all of this kind of thing. And these go by a number of names. So for instance, sometimes physicists will talk about mirror worlds or twin worlds. And basically what they're saying is, let's imagine dark matter that there's basically like a hidden copy of all of the standard model particles. But it doesn't have to be exactly the same. Like we can imagine that dark matter is a little bit different. So maybe it has like a subset of the particles, or maybe it has even more types of particles. We don't know. And this is interesting because now instead of dark matter being just one very simple thing, it can potentially be made up of lots of really interesting pieces. So this gives rise to this notion of a hidden universe, that there's this whole bunch of things that are out there living in this dark matter world. And we really don't know about any of this. So as far as we know, there could be dark matter nuclei, dark matter atoms, dark matter stars and planets. There could even be dark matter aliens, which is a little bit unsettling to think about. But yeah, we just don't know. And of course, there are constraints on some of these things, but there's a lot of possibilities. These collectively go by the name of hidden sectors, these whole groups of particles that interact with each other, but don't really interact very much with us. Apart from just changing the way dark matter looks, though, there's some other interesting possibilities. So for example, if we have a dark photon, theories of particle physics tell us that if I have such a dark photon, there's actually a chance that it will switch into being a regular photon. It's a rare thing, but it can happen. And similarly, a regular photon could have a possibility of switching into a dark photon. What that means is that with these hidden sectors, there might actually be these ways of very feebly communicating with dark matter, producing it, interacting with it in some way. It's not going to be very often something that happens, but it's something that can happen very rarely. So this is the picture of dark matter that I'm going to be talking about for the rest of my talk. As I said, there are other perspectives, but it's still, I think for me, this is a compelling picture that makes us think about what we want to learn about dark matter. Before I move on, and I saw that there was a question about this, and so this may partially address it, but maybe not. I wanted to put this in because this is something that just happened yesterday. So this is very hot off the press. This is a headline from the New York Times. Finding from particle physics research could rewrite the known laws of physics. And this is a really exciting result that involves a particle called the muon, which I said earlier is like a heavier cousin or a heavier copy of the electron. And the muon is an electrically charged particle, and it also has a property called spin. It's not really a good way of thinking about it, but you can sort of roughly imagine if I have a ball that's spinning, it's kind of a quantum analog of that. For our purposes, what is important is that the fact that this particle has spin means that it acts like a little bar magnet. So you probably played with these when you were a kid, or maybe you have kids that have played with them. Has a north pole and a south pole. And if I put another magnet nearby, it can rotate, it can be attracted or repelled. And basically, we can calculate how magnetic these muons are from the known forces in the standard model. And then we can put the muons in like a giant magnet and check whether the magnetism that we predicted matches the experiment. And the answer is that it doesn't match the experiment, and that this is one of the first convincing pieces of evidence that maybe actually we don't quite understand everything about the known particles. And so this is really the first crack in the standard model, or at least one of the first cracks in the standard model. What's particularly exciting for this from the hidden sector perspective is that these same dark photons or dark Higgs bosons that could be out there could be subtly changing the magnetic properties of the muon to explain this experimental result. So this is very exciting. It's still too early to really know for sure. There are experimental questions about what they're doing. There are theory questions about, do we really understand everything about the calculations that we're doing? And it could just be a really unlucky fluke. So we're not at the point of announcing discovery yet, but this is potentially the first window, kind of as unlikely as it seems, into what's going on with dark matter. In the last 12 minutes or so of the talk, having explored some of the ideas of what dark matter could be, I want to talk about, well, how do we actually figure it out and tell what dark matter is? And once again, it's best to go back to something more familiar and make an analogy. So we can ask, well, how do we know the protons are made of quarks? How do we know the atoms are there? And the answer, as crude as it is that we smash them into things. So we take a proton, which is some complicated combination of quarks and gluons, and I mean, this has been done literally in an experiment. You just take them and you hurl them into a chunk of lead, and you see what happens. And basically, the particle will smack into an atom in the lead, and then a bunch of stuff will go off in all directions. And then we try and reconstruct the innards of the proton through the debris that comes out of these collisions. So the collisions allow us to break stuff open and see what's inside, but they also allow us to do something else that's interesting. And this arises from one of the famous results of Einstein's theory of relativity. So those of you who are alums or current students will definitely have fond or not fond memories of dealing with these kinds of collision problems. But mass is a form of energy, and I can take normal forms of energy and turn it into mass, or vice versa. So what that means is that when I have a collision here involving an energetic proton, I might actually make new types of matter, new mass out of this collision. And what this means is that I might actually be making dark matter in these collisions as well. And that's a really exciting prospect, that if we have these very subtle, slight ways of talking to dark matter, then every time we do a particle collision to learn about standard model things, there's a very small chance that we could be making dark matter as well. So perhaps the most famous example of a particle collider today is the Large Hadron Collider, or LHC. Hadron is just a fancy name for a proton or neutron. And this is a collider that does head-on collisions of protons. So protons are accelerated around this ring, one clockwise and one counterclockwise. And this is an enormous accelerator. It's 17 miles long, and it straddles the border between France and Switzerland in the vicinity of Geneva. And if you actually go to Geneva, you can go to one of these farms. The farmers will not like it, I can assure you that. But you won't see anything because it's actually, the accelerator is buried about 100 meters underground. Some interesting facts about the LHC. So the protons are moving at 99.999999% of the speed of light, which is very fast. In order to keep the protons going around in this circle, we have to have huge magnets that bend them. And these magnets need to be kept very cold, so cold that actually the ambient temperature inside of the accelerator is colder than outer space and might be the coldest extended area in the universe that we know about. And there's a lot of really cool stuff about these collisions. They happen, for example, 40 million times per second. So it's a really incredible feat of engineering for a number of reasons. But eventually the protons are fired at one another in specialized sites where there are pieces of instrumentation that record the debris and then try to reconstruct the collision. So this is an example of a detector at the LHC. This is called the ATLAS experiment. And the protons come in each of these ends, and then they meet right in this middle region. And then there's a giant explosion, and then the new particles that are created just go flying off in every direction. Now, to give you a sense of the scale of these experiments, right over here, you might notice something. This is actually 2 adult humans, or at least caricatures of them, standing on the detector. So this gives you some sense of the scale of this. It's something like 40 meters in diameter. There are more people that are kind of walking along it here. And the reason why it has to be so big is that there's so much energy that's released in these collisions that these particles are carrying away that you need to have giant detectors in order to precisely identify them and measure their properties. The detector itself is designed like a sort of cylindrical onion. It's composed of a number of different layers, and each of those layers is good at detecting a certain kind of particle or measuring some property of the particle. So the particles that are produced in the collision originate from this blast point here, and then they go out and they pass through all the layers, and that allows you to reconstruct what they are. So the raw data from this, there are hundreds of millions of readouts in experiments like this, is not very enlightening, but the experiments produce pretty pictures that we can use to try and figure out what's going on. So this is what's called an event display. It's basically a reconstruction of the trajectories of particles produced in a normal collision. So in all of the pictures I'm showing from now on, the beams are coming in and out of the screen. So basically you can imagine that you're like shooting one at the screen and one's coming back at you, and then they meet in the middle and stuff goes out in a perpendicular direction. So notice that all the particles are emerging from the collision point, and there are hundreds or thousands that are produced per collision. But most of the energy is shot in 2 back-to-back directions. And this is the result of conservation of momentum, that there was no initial momentum this way. And so we have some energetic stuff going to the left and some energetic stuff going to the right, and then some kind of piddling stuff in other parts of the detector. This is what just like a normal standard model collision will look like. And then we're interested to know that if we're making dark matter in our experiment, how does that change this? Remember that dark matter is, we should be calling it invisible matter. It's something that we just don't see. It passes right through us. So an example of a collision with dark matter might look something like this. So now instead of having 2 things going off one side, here hitting the detector, one side here going to the detector, there's clearly something that's going this way that just is passing through all the different parts of the detector and not interacting at all with it. And that's the hallmark of what dark matter would look like if there was a dark matter particle going off this way. So this in particular is this minimalist perspective of dark matter, where we have like one dark matter particle. It doesn't do anything that's visible. Sorry if you can hear the trains in the background. So we can try and reconstruct dark matter by looking for these sort of invisible things that are just disappearing into our detector. So this is actually data from a real collision. So you might say, oh, well, you've just discovered dark matter from this picture. But there's a problem. Remember that there are these ghostly particles, these neutrinos in the standard model that also just fly through everything. And so most likely what's happened here is not that we've made dark matter, but that we've made one of these neutrinos or a pair of these neutrinos. They've gone flying off. We don't see them. And so the challenge of looking for dark matter is that there's this standard model particle that essentially fakes it. And we need to somehow disentangle those 2. So a couple of words about this minimalist perspective. First of all, it's been very well studied because it's a minimal and simple idea. But there's really little information in this to go off of because we're just not seeing the dark matter. And so far, we have yet to see any evidence that we've produced dark matter this way. So one interpretation would be, well, maybe we're just not making dark matter in our collider. But the other might be, well, maybe this minimalist perspective is not the correct one. So what happens if we have one of these hidden sectors with a bunch of particles? Well, now we have something more complicated, because instead of just making dark matter, we can actually make a bunch of these particles. Maybe we make a dark photon or a dark Higgs boson. And some of these will be invisible, but some of them will decay back to stuff that we can actually see. So what we end up with is, instead of just having invisible things over here, we see kind of known particles emerging out of the middle of the detector. And the reason why they emerge out of the middle of the detector is because these are still only very weakly interacting with us. So these particles go a long way before they decay. And so the signature of many hidden sectors is that we see some missing stuff, but then we also see these things that are not coming from the collision point that are just sort of mysteriously emerging out of various points of our detector. So one of the things that I and my group do is we think through, okay, if we have a theory of these hidden sectors, how would they look? And indeed, for instance, as we've shown in these work, this is a kind of generic example of what you might see. So there are names for these signatures. They're called long-lived particles. And the reason why they're called long-lived is because they don't come from the collision point like most of the standard model particles do. They go some distance and then burst like fireworks into the middle of your detector. And this is really exciting because there's basically nothing in our known theory of the standard model that can look like this. This is totally weird. So if we can reconstruct it, then that means that we have a really good chance of discovering the physics of dark matter in these colliders. But there's a catch, there's always a catch. And the catch is that these detectors were also not designed to look for this. In fact, the detectors were very specifically designed to look for stuff that's coming from the collision point. And so if the detector components see a burst of stuff hitting it that's not associated with things coming from the collision, then the algorithms might say, oh, that's noise, we're going to get rid of it. Or something weird's happened, our detector is malfunctioning, and throw it away. And indeed, these collisions might not even be recorded and preserved at all. So it could be that there's lots of dark matter that's being produced, and just the experiments that they're currently set up are just losing that information. The last challenge is that this might only happen about 1 in every trillion collisions or less. So we're looking for a really spectacular but very rare process, which means that we really need to be very attentive to looking for these things. So one of the ways that I've worked to address this was by co-founding and co-leading a group called the LHC Long-Lived Particles Community, which is a group of a few hundred theorists and experimentalists that came together to try and see, can we collectively tackle and make sure that we're seeing all of these, we're doing all we can with our equipment. So that's one of the things that we're doing to look for hidden sectors, but I wanted to spend the last 2 or 3 minutes just talking about what we're actually doing at Harvey Mudd. And you might be saying, well, wait, how does Harvey Mudd have a 17-mile, $10 billion accelerator? And the answer is that we don't. But there's a few different ways that we can leverage what we do at Harvey Mudd to try and help discover the physics of dark matter. So one of the directions we can go is to use open source data. So there's this move within the particle physics community for these experiments to release their data in forms that are accessible to the general public. Unfortunately, the form that they release it in is extremely opaque and almost unusable. But these 2 students, Anna Barth and Andres Cook, worked with me during their first year and were actually able to extract real LHC data and do a search for a hidden sector model with a dark Higgs boson and a dark photon. So this is actual data from LHC collisions. And they were able to do this and try and look for evidence for this theory, which they did not find, but they were able to put constraints on that theory. The other option, or another option, is to become an experimentalist. Okay, so basically join up forces with people who do have a detector. And at the LHC, this is hard because there are thousands of physicists working on this. It's really easy to get lost in the muck. So the experiment that we work on at Babar is, at HMC is called Babar, as in the elephant Babar. And thankfully, we haven't been sued yet for having this elephant. It's a much smaller scale experiment. Instead of a 17-mile accelerator, it's only, quote, a 2-mile accelerator at Stanford. And it collides electrons and positrons at energies that are well below the LHC energy, but it actually collides them more often, faster collisions. And that can help you because if you're looking for something that's very rare, you might actually care more that you're colliding them more often than not. So with these students, Jatin Abakusnag, Ina Flood, and Steve Nguyen, we've done several analyses using Babar data to look for hidden sector particles. One of them was recently published in Physical Review Letters and actually rules out one of the popular models for this funny muon magnetic stuff. So we haven't seen any evidence for it, but we were able to basically shut the door on one of the hidden sector theories that involved these muon magnetisms. And what's really remarkable is that using this data, our results are really the best in the world for the scenarios that we've looked at, as we've beaten out all of our competitors just with our little group at Harvey Mudd and some collaborators elsewhere. The final thing that we can do is simulate our own data. So sometimes as theorists, we don't actually want to get into the muck of the detectors and the noise and dealing with that, but we want to look at the big picture. How well are we testing theories of hidden sectors? Are there things that we could be looking for that we're not looking for? And in order to do that, it's better to simulate your own simpler data and make sort of cartoons, which are not 100% of what the experiments will be looking for, but give you a general idea of what they'll be seeing. So right now with this group of students, Mason Acevedo, Albany Blackburn, Victoria Lloyd, and Mavis Stone, we've been working to see how we can better leverage these lower energy colliders to basically replicate the successes of the LHC for some of these hidden sector scenarios and maybe actually do better. So I'll conclude by just summarizing that reason why I like what I do is that we get to use the coolest and fanciest machines in the world, where we take the tiniest objects and smash them together. And we try to do that to answer the biggest questions that we have about our entire universe. So I'd like to thank you, and also to thank my amazing COVID research group. We have been working remotely this year, but I thought I'd put in also a picture of back in the day when we could actually be in person, and hopefully that day will come again soon. So thank you, and I'm happy to take any questions that you might have.
Great, thank you, Brian. I do have a few questions for you. Do all galaxies have approximately the same percentage of dark and regular matter?
That is a great question, and the answer is no. That there are some galaxies that have more dark matter than regular matter. So there are classes of galaxies, for instance, that are called ultra faint galaxies, which are dominated by dark matter. And so many of those tend to be what we call dwarf galaxies. So the Milky Way Galaxy is the largest galaxy in our vicinity. And then there are a bunch of smaller galaxies that are in orbit around the Milky Way Galaxy. And so we see a real diversity of the kinds of galaxies that we see. Now, I guess one other comment is that for a while, we couldn't actually see these ultra-faint galaxies, and this was seen as a threat to the dark matter theory, because our simulations were saying we should have all of these little galaxies that we're not seeing, but as instruments have improved, we've been able to see them, and that's confirmed that aspect of dark matter theory.
Thank you. Does space itself have mass?
That is a great question. Space itself does not have mass, but as far as we know, space itself has energy. And this is getting into something that I didn't really have the opportunity to touch on. But in addition to dark matter, there's also something that's called dark energy. And if you look at the energy budgets, instead of the matter budget of the universe, which is 80% dark matter, 85% dark matter, 15% regular matter, if we look at energy, then actually 70% of the energy of the universe is dark energy, 25% is dark matter, 5% is regular matter. And one of the effects of this energy intrinsic to space is that it leads to an accelerated expansion. So if you have heard of the idea of the expanding universe before, you might think of it as, well, it's kind of like the universe is getting bigger but slowing down because the stuff in the universe is sort of trying to attract itself. And so we sort of have this idea of a gradually, slowly expanding balloon. But what we now know is that the universe is actually expanding faster and faster all the time. And that has to do with the fact that the more you expand, the more space you have. And the more space you have, the more of this dark energy you have. And that drives it to expand more. And that actually leads to an exponential expansion. So we also don't really understand that much about dark energy, but for the purposes of focusing the talk, I focus on dark matter, but if people have questions about dark energy, I'm happy to talk about that as well.
Thank you. Can you provide a reference comparison for the numbers of collisions needed to detect a Higgs boson?
Yes. So right now, we've detected between 1 million and 10 million Higgs bosons at the LHC. So I can't remember the exact number, but Higgs bosons are produced on average every second at the LHC, roughly every second to 10 seconds. the kind of hidden sector stuff I was talking about, you might only be making one every month or every year. So it's several orders of magnitude different, but one of the main limitations of our understanding of the Higgs boson is that we just don't have enough of them. And so actually the Large Hadron Collider upgrading their facilities to increase their collision rate by a factor of 10 with the purpose of producing as many Higgs bosons as possible. So I think by the end, we'll have like 100 million Higgs bosons.
Thank you. What is a dark photon, and is it derived from Maxwell's equations?
That is a great question. So for those who, it's been a long time or don't remember, Maxwell's equations are the equations of electromagnetism that tell you how electric and magnetic fields change over time. Essentially what we're saying is that a dark photon means that there's electromagnetism among dark matter. So there will be a dark set of Maxwell's equations, and that could potentially lead to, for instance, attractive or repulsive interactions but among dark matter particles. The one difference is that in most of the theories that we consider, the dark photon actually has a mass, whereas the regular photon doesn't have a mass. So you need to modify Maxwell's equations a little bit to account for that mass, but otherwise the equations are the same.
Thank you for the explanation. So you mentioned there could be dark planets and dark stars, but if they were in or near our solar system, we would see their gravitational effects, right?
Yes, although that depends on how big the dark planet and the dark stars are and how many of them. So often in theories that have dark stars and dark planets, they are, so by dark planets, often they're referred to as like mini halos or mini clusters. That's the kind of jargony word for them. And usually most of the dark matter is not in those things. And one of the ways that we know this is that I showed a picture of where dark matter is in the galaxy, and it's like this giant ball. Okay? But the visible matter is confined to a disk. And the reason for that is that visible matter, atoms can emit radiation, which causes them to lose energy, and they kind of collapse into a disk structure. So we know that dark matter, only a fraction of it can do that. And so one of the things that people do is they think about, okay, how can we constrain, for instance, these dark matter star or planet models by imagining what if one of them were to come through the solar system? How often would that happen? What would it do? And then we can put limits on it. But there are actually proposals to use atomic clocks that are located at different places on Earth. And if like a giant ball of dark matter planet came through, it would like mess up the relative synchronization of the atomic clock. So there are ideas that people have for things like that.
Great. Our next question, there's been some discussion of primordial black holes as a candidate for dark matter. What's your take on that?
That's a great question. So one thing that I didn't really mention are black holes. And it turns out that black holes have the required attributes of dark matter. So in that case, we might say, oh, you don't have to add a new particle because if standard model particles collapse into black holes and there are enough of them, then it's okay. Now, it turns out that there are very severe constraints on there being primordial black holes. And so actually for most of the mass range of black holes, that's been excluded from different kinds of astronomical observations. But there's a class of black hole masses that are sublunar, so like of order of the moon's mass and maybe 1,000 times smaller than moon's mass, that actually could account for dark matter. It was thought for a long time that that was just completely ruled out, but in recent years, people have reevaluated and found that those constraints were actually not valid. We don't necessarily have great theoretical predictions of how many of these black holes that we make. And so that's currently a challenge, is that we're not able to see whether we actually have that quantity. But there's been a rekindling of interest in primordial black hole dark matter, in part because of LIGO, which is a gravitational wave detector, which has found these merging black holes and found that there's an unexpected population of very large black holes that kind of went against the common wisdom. And so that's caused a lot of astrophysicists to rethink, maybe we actually don't know that much about how black holes are formed. And so I think it's an exciting possibility. I think it's tricky to make it work, but that it's something that people are exploring and that it's worth exploring further.
Thank you. Are there any totally different theories besides from dark matter that account for the evidence of dark matter? Like, are there working physicists who don't think dark matter is a thing?
So the short answer is yes, there are working physicists who don't think that dark matter is a thing. And the most common alternative to dark matter are what we call theories of modified gravity. So the way that I fixed up this problem of things are rotating too fast is that we said, oh, let's put some more mass in there. But it's also possible for you to say, well, maybe gravity doesn't work the way that we think it does. And if I change my equations of gravity, then I can explain that. And there's one sort of the most popular theory is called modified Newtonian dynamics, or MOND. And it's a theory that actually explains very well rotations on galaxy scales. The tricky part about these modified theories of gravity is that we don't just see dark matter in galaxies, we also see it in galaxy clusters. We've even seen evidence of where you have galaxies that collide and the dark matter basically gets stripped away from the visible matter because the visible matter gets like stuck in the middle of the collision and the dark matter keeps going. And so we can actually see spatially separated, like here's the visible matter, here's the dark matter. So some of those things are very hard to explain with modified gravity, and all of the very early universe observables are similarly challenging. It doesn't mean that it's not right, and there are some people that work on that, and maybe actually there should be a little bit more people that work on it just to see, you know, are we missing something? But the vast majority of physicists accept the dark matter interpretation, but that doesn't mean until we actually discover what this dark matter is, we have to also include these other possibilities.
Thank you, Brian. We have time for one more question. We did get quite a few questions about this topic. Does Fermilabs New Discovery about muons imply anything about interactions?
That's a great question. So I didn't really have much time to talk about it, but essentially, like I said, what's happened is that we're measuring this property of how magnetic are muons. And these theoretical calculations have been done with enormous precision, out to 10 decimal places. And the experimental probes have now also gone to 10 decimal places. So we have this string of numbers, and basically in the 9th decimal place, these two things disagree with one another. And it's exciting because basically we haven't seen any disagreement really between our predictions and data. So the fact that we are able to have things with such precision in principle allows us to test whether there are these new interactions. So for example, having a dark photon or dark Higgs boson, these sorts of things, as well as other theories that people talk about like supersymmetry, all of those things could explain this extra magnetism in muons. However, it turns out that there's a part of the theory prediction that's actually really hard to do. And this calculation is the most uncertain part of it. And there's currently disagreement between different theorists, some of whom say it's impossible to reconcile the theory and experiment measurement, and other people who say, actually, we can reconcile the theory and experiment measurement. Right now, the jury's still out on it. And I guess what I would say is that it's not obvious that you can reconcile them, and it's not obvious you can't. Like, it could be that if you dramatically change the theory prediction that you mess up something else, right? So these are very closely interlinked things. And so I think a lot of theorists are optimistic, but sort of cautiously optimistic that there's still some checks that we have to do. Dark sectors or dark matter could be one of the explanations for this muon discovery, but there are also others that it could be. And that's actually one of my main interests with the Babar experiment, is that we're trying to test out, figuring out what's the list of theories that could explain this, and go one by one and check them explicitly and see if we can either discover something or rule it out.
Thank you so much, Brian. We did get a lot of questions. I will be sending these questions to Brian, and then he will answer them for us. I do want to thank once again to Professor Brian Shuve for joining us today and for sharing your knowledge and insights with us. Thank you to our audience for your questions and for attending this event. We will follow up within the next week with a recorded video and presentation material. An announcement for alumni. Alumni April is in full swing. Please visit alumni.hmc.edu and click on the big Alumni April graphic for the schedule of events and registration links. All general upcoming events can be found on our online offerings page using the link included in your confirmation email, or by visiting alumni.hmc.edu and clicking on online offerings. We welcome any suggestions you may have for upcoming events, or if you are interested in hosting one, being one of our Mud Talk speakers, please email us at alumni@hmc.edu. Thanks again for joining us, everyone. Have a great night. We'll see you next time.
Thank you.